This is a functional block diagram of 8085 microprocessor, and this functional block diagram is probably the single most important information for understanding the operation of a microprocessor or microcontroller or any kind of processor. To understand a microprocessor, we have to understand its instruction cycle. And for any microprocessor, uh, this instruction cycle has three main steps. The steps are: first, fetch, and second step is decode, and third step execute. Okay, these are these three are the uh, three steps for instruction cycle. And there's one complementary steps called storage. The first thing we have to look at is the program counter. And this program counter is a 16-bit register which is used to store the memory location, used to store the address of memory location from which the next instruction has to be fetched. And we have to know, we have to understand that uh, unlike uh, unlike microcontrollers which have uh, memories inside, this kind of microprocessors doesn't have any memories inside, and it has to be interfaced externally. Okay, let's suppose that this is the external memory. The content of this program counter will be transferred to this address bus, and this address bus is divided into two: lower byte and upper byte, and these two buses will combine to form a 16-bit address bus. And this 16-bit address bus will be uh, connected, or will be fed this information. This address information will be fed to a circuit called address decoder, and this address decoder uh, will point to the particular memory location which is pointed by this program counter. And if you look at this lower address byte, this is multiplex. This is multiplex between address and data. Whether it is uses address bus or data bus depend on the signal which is provided by this ALE. ALE means address latch enable. If this ALE is high or 1, this bus will be used as address, and if this ALE is 0, this bus will be used as data bus. Okay, and after that the content of this particular memory location which is pointed by this address decoder will be transferred back. while while this while this transfer happens, this ALE has to be 0 so that this this bus will be used as address bus, and this data has to be brought back to its data bus, and it has to be stored inside a particular register called instruction register. temporarily. Okay, in short, this program counter has the or this program counter contains the memory location from which the instruction has to be fetched, and then uh, the content of that memory location is brought to this data bus, and it is stored inside this instruction register for a while. And up to this, we have done this fetching operation. Okay, the instruction is brought, and the next step is this instruction, which is inside the instruction register, is fed into a particular register, not register, into a particular circuit called instruction decoder and machine cycle encoder. This instruction is fed here, and inside the circuit, the instruction is broken down and translated, and it will determine what is the opcode. Opcode means what is the operation to be performed, and also the operand, which register will be used, or which immediate data will be used, which um, memory location will be used. Accordingly, this information is provided to this timing and control circuit, and this timing and control circuit provide or generate this signals according to what is the opcode, what is the operand. And if you look at these arrows, this timing and control circuit provide signals everywhere, literally everywhere. So for example, this timing and control circuit provide signals to LU, to the flag, to the interrupt control, to the accumulator, to temporary register, to the serial IO control, to everywhere, literally everywhere. And this timing and control circuit generates a lot of signals. We have this X1, X2. This X1, X2 is connected to a crystal oscillator, and this is like the heartbeat, and this is like the pulse. This is the main source of signal, and we have this clock out, and this clock out signal is used to give this kind of pulse information to some external peripheral devices. And then we have control signals. Inside the control signal type, we have 4 signals: this read, this write, this ALE, and this IO or memory. Okay, this read RD bar. Okay, this is active flow. Active flow means that if this signal is low, this read operation will be performed. Read operation performed means there will be transfer of data from external memory location to the CPU. And if this write signal is low, writing will be processed, writing will be done. So the transfer is from CPU to the memory location. And for this ALE, we have already learned this is to select whether this lower byte is used as address bus or data bus. And we have this IO or M. Okay, if this signals 1, the data transfer is between the CPU and the IO. Or if it is 0, data transfer has to be between CPU and the memory. Okay. These are all control signals. And we have another category called status. Okay, the difference between this control signal and status signal is that control signals actually controls operations, but the status signals are not controlling. These signals are used to just give information to some external devices. Okay, this S0 and S1, these two signals combine to tell some external devices uh, that the CPU is performing this kind of matching cycle. Okay, if so for example, if these two signals are 0 0, the matching cycle it performs is hold. If S1 is 0 and S0 is 1, it will tell or the external devices that the CPU is performing write. If it is 1 0, it's read. 1 1 is patch. So according to the status of this S0 and S1, it will inform some external devices that the CPU is performing this kind of operation, this kind of matching cycle operation. Okay, and then we have this DMA, direct memory access. This for this DMA we have three signals: this hold, acknowledge, and then ready. Okay, these signals are used to exchange information, are used to transfer information, um, transfer memory information between memory, some external memory, and some peripheral devices without the use of CPU. And we have reset in, reset out, and these resets are uh, used to point or stack pointers to some predefined memory location. So for example, in most cases, if preset signal comes, our program counter points to the so for example 0000, the initial location, and the instruction starts. Okay. Up to this we have decode operation, and then we have this register select. Okay, we have understood what operand is going to be used, and accordingly this register select can select the particular register which is inside the instruction. This register select is used to select register which is inside the instruction, and this multiplexer provides the path to transfer the content of that particular register back to the data bus, and it will be transferred to accumulator and temporary register according to the type of instruction. And these are the registers which contain the operands, and these two operands will perform the instruction inside this ALU. And this ALU will give the result. The result is either stored inside the accumulator or some register or some memory locations. It's according to the instruction. It's not just storing the instruction, not instruction. The result of the operation also affects this flag register. So for example, if your answer gives 0, this flag, the zero flag will be set. Likewise, all the flags will be affected by the result of the operation, but it also depends on the type of instruction. So we have executed, we have done the execution, and then storage. Okay, and then we have this block, serial I/O control, and this block is uh, used to transfer data between the CPU and some external devices serially. Okay, this is for serial data transfer. SID means serial input data, and this is the path for serial output data to be transferred from this CPU to the external devices externally, not externally, serially. And then we have this interrupt control. Interrupt is kind of like signal which is used to break the sequence of instructions. So for example, let's suppose that this is the memory location and it stores the instructions. So for example, the CPU performs some operations sequentially, and then suddenly some interrupt signals coming, and according to that, this program sequence has to be break, and and the sequence has to go to somewhere else according to the interrupt service routine vector, and then it will perform this it will perform the interrupt service routine, and it will be brought back to the original memory location from where it jumps from. How do it know that it has to jump to this memory location? Okay, it is with the help of this this 16-bit register called stack pointer. This stack pointer, while doing this kind of branching operation or push and pop operation, this stack pointer stores the memory address. Okay, memory address to which this instruction has to come back. The step of execution has to come back. And one thing we have to know is that we have this incremental decremental addresslets, and the CPU performs the instruction sequentially, and it is with the help of this incremental decremental addresslets. How? The content of this stack pointer will be incremented by 1 just after it is the dice this instruction has been fetched. Okay, if the instruction has been fetched, this instruction decoder will increment the content of this stack pointer by 1, and so after executing the data, the program counter will point to the next memory location. So, and this way it performs the instruction sequentially. Yeah, we have this general purpose registers. In addition to general purpose resistors, we have some resistors called W, Z, and temporary resistors. Why this temporary resistor used? What is what are their importance? Let's look at a situation where there's two resistors, and these two resistors has to exchange their contents. There's some instructions which do this kind of operations. So in this case, the content of A will be transferred to B, and B will be the content of B will be transferred to A. So what is the first thing to do? So for example, if the content of A is loaded to B, then what happens? The content of B will be lost. So, but we cannot lose the information. So how can we perform this operation without losing? We have to use another resistor. Call this temporary resistors. So for example, A has to first transfer its data to this temporary resistor, and then B will transfer its data to A, and then this content of temporary resistors will be brought back to B. This is how this kind of exchange or this kind of instructions are performed. I think we have covered almost everything, so we can wrap up here.